Okay, so where we left off was we said, all right, if at every trial we have this d, let's say, which we set equal to 1 if the trial is a success, and set it equal to 0 if a trial is a failure, then if we take the number of successes to be x, then x is the same as taking the sum of these d's over all the trials. And there was n trials and over all the trials. So we said, all right, then divide x by n, and that'll tell us the proportion of successes, and we can use that to estimate our p. So let me put a hat on the p to denote our estimator. There it is, p hat is x divided by n, which is 1 over n times the sum of the d's. So what is this? This is just our sample mean. So it's just d bar, if you want to call it that, to continue with the notation we used before. What is the advantage of this? The advantage of this is that it's a sample mean, and so we can make use of the central limit theorem, which says that this quantity is approximately normal. So p hat is approximately normal with mean p, which is the quantity we're interested in, and standard deviation p. So we know the standard deviation because it's just the square root of p, 1 minus p divided by n, if we know p, of course. But it's a function of p. So if we want to set up our standard normal variate, there it is. This takes the place of our old x bar, this takes the place of mu, this takes the place of our sigma squared, and their division by n, and we're back to where we were before, and this is approximately standard normal. And this is what we had with the continuous variables. Now, the distinction, what makes this more complex, is that the same p that we're interested in appears as in the mean, and it appears in the standard deviation or the variance. And that's what makes this a little bit more complex. Now, one solution, and this is called the Wald solution, is to say, oh, okay, I'm only mainly interested in the mean. So let me get rid of this complication by replacing the unknown p by what we've estimated in the sample. So let me put the p hats down there. That's called the Wald estimator. There is another way around this, and that is to say, let me not make use of the standard normal. Let me not make use of the central limit theorem. Let me rather do something that's called the exact method. Okay, and just make use of the fact that this is distributed as a binomial. We'll come back to this. There's a third option, and that is the one that I prefer. And that is to not make use of the Wald and just go back to basics here. And this is called the Wilson method. So the Wilson method for giving us confidence intervals on p makes use of the fact that z is approximately normally distributed. So for example, we can make this statement. That statement is approximately true that 95% of the time our standard z is going to be between minus 1.96 and 1.96. And as I said, 95% of the time. So remember, this is the value you went to bed with. You said to yourself, z is between minus 1.96 and 1.96, 95% of the time. Okay, so there it is. Now, there are a couple of messy things in here. One is we've got two inequalities to deal with. So that's one, and there's the other inequality. And the other is we've got this square root to deal with. So what Wilson did was very, very clever. He said, all right, let me just square everything. So if you square everything, you get rid of the square roots, and you replace the two inequalities by a single inequality. But yet you retain the value of the statement. So there it is. So that's what Wilson said. And the answer was find me the p's for which this inequality is true. So let me multiply through by this and multiply both sides, and so there it is. Approximate confidence interval, solve for p's that satisfy this inequality. So there it is. Now I can subtract this quantity from both sides, and there it is. So there's what Wilson said is find the p's for which this quantity is less than or equal to 0. Now, what is that quantity? Well, look at that. That's just a parabola. So let me clean off this thing. So what do parabolas look like? Parabolas look something like this, maybe. And so there's the origin. And what we're asking for is when is the parabola less than or equal to 0? So down here it's less than or equal to 0. So we want to know the p's that lie in there. And that's the Wilson confidence interval. Now, of course, we're not going to do all these calculations every time. What we're going to do is we're going to ask Stater to do it for us. So let's do that. So here I've chosen 7. So I've chosen 7 variables from our Framingham Heart study. And these 7 variables are all 0, 1 variables. And here are the answers for the proportions of these variables equal to 1 when we look at all 4,434 people in the study. So for example, we have that deaths are approximately 35% of the people. Angina is about 16%, and so on, down to hypertension is 73%, and our old friend diabetes at the first visit is roughly 2.5–3%. Now, this is for the whole population. So these are the population values. Remember that we're going to pull the same trick we've done before, namely take a sample from this population and use that to judge how well our estimator does. So, for example, we'll take a sample of 20 observations, and let's see what happens with when we asked for the confidence interval for the Wilson. So we asked for the Wilson confidence intervals. And so here we have 20 observations. Now choose one of these, and then our 95% confidence interval would apply to that one. So for example, if we look at death, we get that the p-hat is 0.25. There's the standard error. So that our 95% confidence interval, the Wilson confidence interval, 95% is between about 11% and about 47%. So we're between 11 and 47%. And let's see whether that captures the true value. We have a 95% chance of capturing the true value, and there's the true value. The true value was 35%. So yes, in this case we were successful. So this was successful. Now we've got to be careful when the mean is very, very small. In this case, it can't be smaller than 0. When the mean is very small, or when it's very, very large, we've got to be careful, and some of these things run into problems. So for example, here they had to clip this. It says the Wilson interval was clipped at the lower point, so it's really smaller than they really would like it to be to satisfy this 95% confidence interval. Now, had we not asked for Wilson, what we would have gotten was the exact. So this is the default. I didn't ask for anything, so there's nothing here. So the default is to get the exact. Now, this is a bit of a misnomer, exact. It's a sales pitch so that it makes it sound more precise than it really is. It isn't exact. It uses the binomial distribution instead of the asymptotic normal approximation. So in that sense, it's better, but it doesn't give you the 95% confidence interval. It gives you something which is at least 95%, but it could be 96, 97, 98, 99, 100%. It can be any of the above. So it also runs into problems when you have 0. So I wouldn't recommend this one. It's conservative because it gives you at least 95%. and it also runs into problems when you've got small numbers. So the other one is the walled, and when you have huge numbers, there's not much difference between any of these actually. But here's an example. Let me show you an example. Now, what are these data? These that you see in front of you are based on about 4 million, so it's 4 million singleton births in the USA. All right, and I'm looking at the proportion males. So this is singleton, be careful. So it's excluding twins and stuff like that. Okay, so here I'm looking at the proportion male, and the overall proportion male is 0.513. That's that line down there. So 51.3% of all births in that particular year were males. And this is typically the value one gets from year to year. We don't vary too much around that. Okay, now what I did was I said, all right, let's look at it as a function of gestational age. So for example, this one zeroes in on gestational age 26 weeks. So just those kids, okay? And what proportion of them are males, and so on. And that's what these numbers are. That's what these little circles are in the center here. Those are the proportions for male for each gestational age. Then what I did is I added plus or minus 2 standard error lines. So these would thus be the walled. So these are the walled intervals. Okay, and that's what these intervals are. Okay. Now, what are we seeing here? Well, the first thing we see is that when the intervals are very, very wide, that means you've got a small n, so that when the intervals are very tight, you've got a large n. So most of us are born roughly in this area here, where the n is very, very small, where the confidence intervals are very, very tight. Number one. Number two, I don't know that I would trust these records for this end of the scale. And I don't know that I would trust these records at this end of the scale either. So if I had the option of believing these or maybe possibly admitting to a clerical error, I think I would probably go with the latter. But anyway, so even within this region, so let's say inside here, what are we seeing? What we seem to be seeing is that down here, relative to the 0.513, relative to this line, down here, we have a preponderance of males. And not only is it just suggestive, but none of these confidence intervals, here's one, the one at 26, does cross this line. But none of the others cross that line. So down there, we've got a preponderance of males. Up here, to the right of 39 weeks, we have a preponderance of females. And it looks like it's significantly so. Now, the question is, why? Why is this so? Why are we seeing this sort of behavior that looks something like that? And the answer is, I've been asking that question for 20 years, and I haven't heard a satisfactory answer as yet. Maybe you have one. Maybe this doesn't happen in your part of the world. It'll be interesting to hear. But bottom line is, these are the kinds of inferences one can make with dichotomous data.